So the topic of our Cram session will be focused directly on hacking some of the most foundational components, yet often confusing and most intimidating problem types when we actually run into them on our day of the exam when we're in the statics session, especially when we're compounded by all the time constraints that we have on exam day. So that topic and problem type we will be cramming on today, specifically is centroids. This topic does follow under statics once again, and there is a new version of the NCES reference handbook. We're at 9.4, version 9.4 now. The pages changed slightly. Everything, equations, symbols, the tables, all those formulas we need to know for statics can be found on pages 67 through 71. So if you do want to reference those as we make our way through the workshop, feel free to do so. I'll be showing you some screenshots, so don't worry if you don't have that in front of you. So what is statics? Statics is an area of engineering mechanics that studies the effects and the distribution of forces on objects which are and remain at rest. Now, these forces are assumed and assessed as if no deformation of the object actually occurs. Or in other words, one of the trigger words in statics, it means the body is rigid. There's no deforming. Now, dynamics deals with objects that do not remain at rest, while mechanics of materials deal with objects that actually deform under forces and loads. So, what is a centroid? The centroid of a center of it, or also known as the center of area of a geometric region, is the geometric center of an object's shape. The centroid is not an actual physical product, but rather it's a set of coordinate values, x, y, and z, if you're in a three-dimensional space, which we're not going to be, but just to mention that, it's a set of coordinate values, and it's measured relative to a specific reference point, typically the origin, or the coordinates 0, 0, 0 of the Cartesian coordinate system that you implement in a convenient reference point. So some problems will have it stated, while in your practice, you can really put that origin wherever you want to make it convenient. But for the exam and for today's practice problems, the origin will be established for us. Now, for many shapes, this location often occurs inside the boundaries of the region. However, in some situations, you may actually compute the centroid coordinates at a position that's outside of that boundary. And I'll show you an example tonight where this actually occurs. So the centroid occurs outside the physical object. So what I like to do now is just get into working some problems while learning the concepts that revolve around the top of the centroids as we make our way through them. So here's our first problem statement. The location of the centroid from the origin of this composite T-section illustrated below is most close to what? Now, the first step in working centroid problems is to actually classify whether the object or the region we are working is discrete or if the region is continuous. Now, a discrete region is an area that can be broken up into several subregions composed of simple shapes, such as rectangles, circles, triangles, and parabolic segments, with known or easily determined areas. You can also easily express the centroids of these regions based on the dimensions of that region. Now, a continuous region is any region that isn't classified as a discrete region. This region is normally enclosed by a complex or irregular shaped boundary. So just envision a squiggly lined object that's all crazy looking. That's going to be a continuous, complex boundary type of region. Now, to determine the centroid of a continuous region, you actually have to define that squiggly line boundary, or whatever the boundary is, by using some type of mathematical function, and then we would employ basic calculus and integration techniques to actually determine what the centroid of that object is. But like I said, it's all complex, all these continuous regions, but for the purposes of the FE exam as well as the Cram session right now, we will be focusing on working with problems that require the assessment of just discrete regions with clearly defined geometric relationships. So back to our problem. Now, we've been asked to determine the centroid of a discrete region. We can classify this object as a discrete region by quickly observing that it can actually be broken up into several subregions composed of very simple shapes. Now, if we get to this problem on the exam and we determine that it's a discrete region, this is a good thing. Means we're kind of on the right track, because the NCES confirms that we're on the right track, because it provides us the discrete region formulas within the reference handbook, whereas it doesn't provide us the continuous region formulas. So if we determine that this is actually discrete region, then we're on the right track. If you can't determine that it is, you got some problems and we got to figure it out, all right? Now, flipping back to page 67, if any of you do have your reference handbook, that's version 9.4, and if you have 9.3, it's going to be somewhere in this similar area. But if you flip back to page 67, version again 9.4 for computer-based testing, we can locate two formulas we will use to help us quantify the results of our analysis of these types of discrete regions. Now again, a discrete region is a type of region made up of a combination of shapes referred to as subregions. Each subregion has its own individual area, has its own centroid calculation that is usually fairly simple to compute. Now we can then combine these subregion properties to compute a single centroidal location by using these formulas that you see highlighted there. Now, if we take a closer look, there are some pretty important nomenclature that we probably should define up front. Now, X sub AC and Y sub AC is actually the centroid nomenclature that the NCES uses. So you might be used to seeing Y bars, X bar, it's all the same. You might see XC, YC. I kind of use it all interchangeable throughout this Cram session, but that's what they use for their nomenclature. Notice how this formula isn't giving us a third dimension, that Z. This is actually should tell you that it's safe to know that you're not going to encounter any centroidal problem in 3 dimensions on the exam. So if you are practicing problems and you actually hit some type of 3-dimensional centroidal problem, don't even worry about it, because the NCES doesn't even provide that type of formula inside its reference handbook. Now, M sub A Y and M sub AX is the first moment of the area, or first area moment. The primary application of the first moment of area is to calculate the coordinates for the location of the centroid, as you see, and that's why it's in this formula. Now, I don't particularly like this notation or even having it defined as part of the centroidal formulas. Rather, I like to define the first moment of the area as the sum of all the products of the area and centroid of each subregion defined. So in other words, in these formulas, X sub n and Y sub n are the distances from the origin to the centroid of the subregion we're working, measured parallel to the X or Y axis respectively. Now, as we work our way through these practice problems, you will see me flash the original formula with the first moment of the area nomenclature, but I will always use the summing root exclusively. It's way less confusing, and plus it's part of my 7-step process that I'm about to lay out for you. And lastly, A is defined as the sum of all the discrete subregions we defined in our analysis of the object. So what is the process in defining an object centroid? Now, it all starts with a centroid coordinate table like you see right there. We construct a table for each coordinate, so one for the x coordinate and one for the y coordinate, or you can just combine them like I do in practice, but for the purposes of learning in this Cram session, we will keep them separate. Then what you do is run through a 7-step process as I show right there. You list all the areas, you calculate the areas for each region, and then you keep running through until finally you have it all filled out and you're able to compute the centroid coordinate using the formulas that were given. Now, this is the exact process that I personally use, and this is the actual process that we want you to use to tackle these types of problems, because if you use this 7-step process, number one, it's not going to take very long. It's going to take long tonight as we walk through it, but you're going to have this process so dialed that no matter how complex the object is that the NCES throws at you, when you go through these 7 steps, you'll have it dialed so hard you'll be performing at a level that far surpasses anybody else using any type of process. So just follow along with us tonight. Again, take notes, follow along in the practice problems. But at the end of the day, I want to make sure that you have this in your mind and you don't have to refer back to it. You can just perform it. All right, so again, we are given a T section with its stated dimensions there in millimeters. And our task is to find the centroid of this area. So let's go ahead and do that. Our first step is to list all of the areas that make up the discrete region. Now, for illustration purposes, what I did was I color-coded each shape. There are 2 that we will use in this problem. Now, each subregion has its own area. It has its own centroid, which when combined and taken into account, help us define the centroid of the composite structure, the object, or whatever you want to call this. So we can break these subregions out as such and list them out in our y-coordinate centroidal table. So region 1, our green region, is a rectangle, and region 2, our purple region, is a rectangle as well. Now, one thing I want to note, you need to be quick to recognize symmetry in these types of problems. In this case, the y-axis falls in the center of this T-shape, and with the object on either side being equivalent with the other, it's a mere replica, giving us an x-coordinate of our centroid as 0. Now I can go through all the dirty work to figure this out. I can do an x-centroid coordinate table, show you all the work, but it's just going to be a waste of time, and there's absolutely no way you should be doing that on the exam. So I just want to tell you one tip, just recognize symmetry so you don't have to go through that mess. All right, let's move on. So step 2 of this process requires that we calculate the area for each of our regions. Now, if we grab our NCES reference handbook, we flip back to the statics section. Pages 69 through 71 will have a few tables defined with the characteristics of a number of simple shapes that we will encounter. The first column will define the shape, whether it's triangle, rectangle, or etc. And the second column will give us the general formulas to determine the area and the centroid of that shape. Now, this is definitely going to come into handy. Our first subregion is a rectangle, so we will use the information and formulas highlighted right there in green. And taking those formulas back to our problem page, we have a region 1 being defined, the area being defined as base times height. And with a base of 100, a height of 20, we define the area as 2,000, which we place into our y coordinate table as you see right there. Now going back to our reference handbook, once again, we are going to be dealing with a rectangle in our second region. Again, we're going to use that same information, those same formulas we just used for area. We're going to bring that back. We have a base this time of 15, that's backwards, but the base is 15, the height is 150 for a total of 2,250. And again, we plug that appropriately into the coordinate table as you see right there. All right, so now we can hop down and continue to step 3, where we will calculate the distance from the origin to the centroid of each shape we have defined. So starting with region 1, we know that the centroid will be some distance y sub cg from the x-axis. And again, we're taking this centroid from the origin. So that's always important to see that the origin, right, in this case, is located at the very top of this object. So that centroid is going to be y sub cg from the x-axis. Flipping back to our tables, once again, we see that the formula for the y centroid of a rectangle is h divided by 2, or the height divided by 2. Bringing that formula back over and plugging in our values, we get 20 divided by 2 is equal to 10. So we plug that value up there into our centroidal coordinate table. All right. So now moving on to our second region, we know that the centroid will be some distance y sub cg once again from the top of its shape. Now flipping back to the tables, once again we will use the y-coordinate centroid of h divided by 2. We'll pull that back. We'll plug in our value of 150 divided by 2. And we'll come up with a centroid of 75 millimeters from the top. But that's not our centroid from the origin. We have to recognize this. And I promise you that you'll get this problem wrong, obviously, but under time conditions, this is a very easy mistake to make. It's not the correct answer because we want to, again, go back to the x-axis. If we don't properly calculate that, all of our values within our coordinate table will be wrong. So in this case, the top of region 2 actually starts at the bottom of our first region, which is 20 millimeters. This means that we need to actually add that height of 20 to get the full distance back to the origin. So you see there ycg, y sub cg plus h1. We plug in those values, and we get a centroid back to our origin of 95. Now moving on to step 4, for each individual region, we now need to take our second column, the area. We have to multiply it by our third column, which is the distance from the origin, and plug this product into our final column in the coordinate table. So we multiply 2,000 times 10, as well as 2,250 times 95, and those are the values we get right there in our very last column. Now for step 5, we sum all the areas that we have defined up to this point. And doing so, we get a value of 4,250. For step 6, we do the same, summing all the products that we just calculated in step 4. And we get a value of 233,750. And that brings us to our final step, where we now have all the proper data defined so that we can actually calculate what the y-coordinate of this centroid will be in this T section. So once again, I want to just constantly flip back to this page. So if for whatever reason, come exam day, you fail to recall it right off the top of your head what the formulas are, page 67 are going to identify them for you. So bringing those back over to the problem, I just wrote those down there in the bottom right corner. We know that we are only concerned right now with the y coordinate. We know that the x coordinate sits at 0, right in the middle of the object. So remember that A in this formula is simply the sum of the subregion areas, and that we don't want to use the first moment of area when it's defined as m sub a sub x, but rather as it is defined in our coordinate table and the second half of the formula we are using right there. So I kind of broke up the dotted lines there on the bottom. That second half, the second dotted, that's the formula I want you to use. Don't worry about the m sub a sub x. Now the numerator in this formula is the value we got in step 6 when we summed all the area centroid values for each subregion. So plugging those values into our formula, we get a y coordinate for the composite object, this T section, that is 55 millimeters from the origin. So completing this problem, we can now define y bar, y sub c, y sub ac, whatever you want to call it, whatever nomenclature you're comfortable with. But we can now define it as 55 millimeters from the origin. And that's all there is to it. This was a fairly simple, straightforward process or problem. I just wanted to walk you through the process, and now I'm going to get you into a little bit more complex scenarios. And if you're able to actually solve this next problem, if you get the process dialed in, you're going to be set come exam day no matter what they throw at you. All right. So the location of this centroid of the composite object illustrated is most close to what? So here we have a more complex object we're working with. We have multiple subregions that can be observed. So this is actually a good thing. That means that we are working with a discrete area. But we have a hole punched right in the middle of this thing, which is really going to complicate some things. I mean, from the way it looks, some of this can't be determined by a simple formula. Some of these subregions can't be determined by simple formulas. At least that's from the way it looks originally on the onset. But really, as I'm going to show you, it's not that complicated. Just follow the 7-step process and you're going to be dialed. So let's go ahead and run through that. So our first step is to list all of the areas that make up the discrete region. So for illustration purposes, once again, I color code each shape. There are going to be 4 in this particular problem. And each subregion has its own area, has its own centroid, which when combined and applied using the proper formulas allow us to define the centroid of the composite object. So we can go ahead and break these subregions out, as I show right there, and list them into our x-coordinate centroid table as such. So region 1, our purple region, is a half circle. Region 2, our yellow region, is a full circle. Region 3, our green region, is a rectangle. And region 4, our orange region, is a triangle. So we have some nice simple shapes to work with here. Now, one thing I want to note, again, you need to be quick to recognize symmetry. In our last problem, we had a symmetric shape that fell smack dab in the center of the y-axis, and that allowed us to quickly define the x-coordinate for that centroid as 0. Now, in this case, the object is much more complex and everything but symmetric. Therefore, there will actually be 2 coordinate tables that we will need to develop. So let's go ahead and move on. Now, step 2 of this process requires that we calculate the area for each of our regions. And again, if we grab our NCES reference handbook, we flip back to pages 69 through 71, we're going to find a number of shapes and formulas that are given to us, where that first column is going to show us the shape, whether it's a triangle, rectangle, or whatever it may be, and the second column will give us the general formulas to determine the area and the centroid of that shape. However, I'm going to tell you right now that not every geometric shape is defined for us, as we will see first thing in this problem. Now, our first region, our subregion, is the half circle. There's no information provided to us in the NCS reference manual directly giving us the formulas for the area or the centroid of a half circle. However, we know that the area of a circle is pi r squared, which means a half circle will have an area of pi r squared divided by 2. So knowing that and plugging in the proper dimensions, we find that the area of the half circle is 5,645, which we place also into our x centroid coordinate table. Now, for the sake of time, I want to obviously save your time, get through more practice problems. We're going to cycle through all these steps without referencing back to the NCS reference manual, as I believe you will be capable of doing on exam days, just recalling what these areas and centroids are, because you're going to be given discrete regions with very simple shapes. So I trust that you're going to be able to recall them right off the spot, since we've been working with these types of shapes, obviously, since grade school. So now we know that the area of a circle is pi r squared. So for region 2, we plug in our dimensions and we get a value of negative 5,026 and plug that into our coordinate table. Why is that a negative number? Why do we have negative 5,026 as our value here? It is a hole. It is an empty space in this object, and we need to account for that. So when we're working with a strangely shaped discrete region, as we are in this particular case, it's most convenient to overestimate an area with a simple shape and then subtract another simple shape from the calculations to account for that overestimation. So in this case, we have if you look at the original object on the left, there's only a small portion of purple right there. But we actually defined it as a half circle. In the same way, we define that green section as a full rectangle. Both of these are overestimations of what they actually contribute to this composite object, because both have a portion of their area cut out by that circle. So what we're doing is taking the full area of the half circle and then the full area of the rectangle, and then we're subtracting the full area of the circle cutout to account for those overestimations. Now I'm going to tell you right now, many are going to hit this type of problem on the exam and just flop. They're going to see this complex problem that has all these cutouts in it, and they aren't going to even know how to proceed, making this problem impossible to complete, since you will never be able to define the area of or centroid of a partial half circle or partial rectangle. It's just not possible, especially in the time you're given. So the important lesson is this: you can add or subtract regions from your estimated shape as long as you apply the correct sign to the area of the region when you calculate it. Areas being subtracted are always negative, and that's why we have this negative sign applied to this value right here. Now on to our third region, which is a rectangle. We know that the area is base times height. We plug in our dimensions. We find that this area is 9,600. And then finally for region 4, that's our triangle. That area of a triangle is base times height divided by 2. We plug in our values and we get an area of 3,600. So now we can actually move on to step 3, where we calculate the distance from the origin to the centroid of each shape we have defined. So starting with region 1, we know that the x-centroid will fall at the center of the half circle as it lies on the x-axis. And this point is located 60 millimeters from the y-axis. Now for region 2, same as with a half circle, the x-centroid will fall at the center of the circle as it lies on the x-axis. Again, this point is located at 60 millimeters from that y-axis as well. Now our region 3, our rectangle, the x-centroid will fall at halfway point of the base width, and this point is located at 60 millimeters as well. And finally, we got our region 4, our triangle. This one is a little different from the others as its x-centroid coordinate is located at a third of its base width. So if we plug in our dimensions, 120 divided by 3, we find that that centroid on the x-axis will be located at 40 millimeters. Now with all of our areas defined, we can now go to step 4. For each individual region, we now need to take our second column, our area, we need to multiply that by our third column, the distance from the origin, and we need to plug this product into our final column in the coordinate table. Now doing this, we get the values of, as you see there in our big values, in our final column. Now take note and notice that our negative value carries through in the region 2, in that circle row. If it doesn't carry through, if you don't carry that negative number through, you're definitely going to get this problem wrong. Again, a very simple mistake to make on the exam. Very simple. Now for step 5, we sum all the areas that we have defined up to this point, and when we do that, we get a value of 13,819. All right, for step 6, we do the same. We sum all the products that we calculated in step 4, and we get a value of 757,140. And that brings us to our final step where we can compute our centroid coordinate, our x-centroid coordinate. Again, if we flip back to page 67, I'm going to just keep pounding this into your heads, guys. But page 67 is your savior if you forget what the centroidal coordinate formulas are. Again, they're highlighted. And I bring those back over to our problem. And we know that right now we're only concerned with the x-coordinate of this particular centroid of this area. So what I'm going to do is simplify it, get rid of that first moment of area nomenclature. And then I'm going to plug in our values. And I'm going to get an x-coordinate of 54.8. So we can now define the x-coordinate of our centroid is located at 54.8 millimeters. So that's our first table. Now we got to actually figure out what our y-centroid coordinate looks like. So we're going to have a y-centroid coordinate table. All right, so step 1 is obviously to list each of the areas. We've already done that in in our x-coordinate, so we don't have to rehash that. And we can move on to step 2 of this process, which is to calculate the area for each of our regions. Again, we've already done that in our x-coordinate table, so there's no need to rehash that work. We have all the values defined. We just plug them into our coordinate table as such. So now we can move on to step 3, where we calculate the distance from the origin to the centroid of each shape we have defined. And starting with region 1, we know that the centroid will be some distance y sub c from the bottom of that shape. But we can't fail to account for the height of the rectangle, which sits right on top of the x-axis. and that's 80 millimeters. So if you see between the exploded view of this object and the actual object, I've kind of defined what this centroid will look like. It's YC sub 1 plus 80. We plug in our radius, and we get a value of 105.4. So moving on to our second region, we know that the y-centroid of a circle resides at its center point location, which in this problem falls at 80 millimeters from the x-axis. Now our third region is a rectangle, which has a centroid that is located at half its height, which is 80. So taking half of this gives us a centroid located at 40 millimeters from the x-axis. And finally, we have our triangle region with a y-coordinate of its centroid falling at 1/3 of its height. But listen up here, don't miss this minor detail, which could be catastrophic come exam day. Notice the negative value for the height, which results in a negative centroid value. Now this is because the shape falls below the x-axis, and since we are finding the centroid relative to the origin as it is drawn, we must not fail to recognize this. So if you were to put positive 60 there as the height, all your calculations would be absolutely wrong. So that's a little nugget again, just pay attention to where that origin is. And if it's below, you definitely need to account for that negative sign. Unless everything's below, then it's not going to matter. But in this case, we have things above, things below, so we got to account for that. Now moving on to step 4 for each individual region, we now need to take our second column, the area, once again, and multiply that by our third column, the distance from the origin, and plug this product into our final column of the coordinate table. And in this case, we get a bunch of big numbers once again. Now for step 5, we sum all the areas that we have defined up to this point. Doing so gives us a value of 13,819. And for step 6, we do the same. We sum all the products that we calculated in step 4, and we get a value of 504,903. And that brings us to our final step, where we now have all the data we need to define the y-coordinate for the centroid of this composite object. Once again, what page do we find these formulas on? This is page 67. But we already got these formulas written out on our practice problem from when we did the x-coordinate. So after a quick rewrite, just to clean up that formula, we can plug in our values and find that our y-coordinate for our centroid is 36.5, which now allows us to define y sub c or y bar, whatever you want to call it, as 36.5 millimeters. And that's the coordinates of our centroid for this complex object is 54.8 and 36.5. All right, so let's hop into another practice problem. Now, the location of the centroid of the object illustrated below is most close to what? Now, the first step in working centroid problems is, again, to classify whether the object or region we are working is discrete or continuous. Now, I know I've repeated this a number of times, but through repetition, we'll never forget it. Remember that, though, for the purposes of the FE exam, we will be focused on working with problems that require the assessment of discrete regions only. Those have clearly defined geometric relationships. We don't have to integrate. We don't have to use calculus. Now, we can classify this object as a discrete region by quickly observing that it can very, very easily be broken down into several subregions, simple shapes. Again, this is a good thing. We're on the right track. This is what the NCES wants us to see. If we're for some reason seeing a continuous region here, we need to go back and kind of just reassess our learnings of each region so that we can move past that and on to the proper process of analyzing a discrete region. So our first step, again, is to list all the areas that make up the discrete region. I've highlighted them there, or kind of color-coded them once again. There are 5 in this case. Now each subregion does have its own area, has its own centroid. And when we combine them for the composite object, we're actually going to define the centroid of that object, the structure, whatever you want to call it in this case. So again, we can explode those subregions out, as I show right there, and we can list them all in our y-coordinate centroid table as such. So in this case, all the regions are actually rectangles. And one more reminder, remember, it's very important that you quickly recognize that this object right here is symmetric. There's symmetry. And in this case, again, the y-axis falls in the center of this shape, with the object on either side being equivalent with the other. So this gives us an x-coordinate of our centroid as 0. Again, we can go through all the mess of trying to determine what that x-centroid is. It'll come out as 0. But I'm just telling you, save your time, save your work, save the stress on exam day, pay attention to symmetry, and just work, in this case, on determining what that y-centroid is. So let's go ahead and move on. Now calculate, step number 2 requires that we calculate the area for each of our regions. Again, if we grab our NCES reference manual, that's version 9.4, pages 69 through 71 are going to give us tables of some very friendly shapes. Again, that first column is going to define our shape. That second column is going to give us the formulas that are relevant to that shape and define the area as well as the centroid. Now again, all of our subregions are rectangles, so we will use the information in the formulas that is highlighted right there in red for each. So that's easy enough. Taking this formula back to our problem, we have a region 1 being defined, the area being defined as base times height, with a base of 3, with a height of 1, and a total area of 3. Now we just continue to cycle through each region to determine its area using the basic formula of base times height. So region 2 has a base of 1, a height of 3 for a total area of 3. Region 3 has a base of 8, a height of 1 for a total area of 8. Region 4 has a base of 1, a height of 3 for a total area of 3. And finally, region 5 has a base of 3 and a height of 1 for an area of 3. Now you didn't even need to do region 4 and 5. If you recognized the symmetry, you would have known that region 1 and region 2 are the same dimensions. They're symmetric with regions 4 and 5. So you could have just plugged those numbers in, but just for illustration purposes, I went through calculating them. All right, so now we can move on to step 3, where we will calculate the distance from the origin to the centroid of each shape that we have defined. Now, starting with region 1, we know that the centroid will be a distance that's half the height of that region. So we can plug in 1 inch, divide that by 2. We know that the centroid is located 0.5 inches from the x-axis. Now moving on to our second region, we now know that the centroid will be some distance y sub c prime from the bottom of its shape, from the x-axis, plus, so we have to actually include the centroid to the bottom of its shape plus the height of region 1, since it is between it and the x-axis. So you can see over there under region 2, under the title, between the table and the exploded view, yc prime is equal to 1 plus h divided by 2. That 1 is the height of region 1. So plugging in our value for our height, we get a centroid from the x-axis of 2.5 inches. Now moving on to our third region, the centroid will still remain at half the height as all the rectangles, but it's also elevated 4 inches from the x-axis. So we have the height of region 1, we have the height of region 2, which is 1 plus 3 is equal to 4. So we have to account for that. Plugging in our dimensions, we find that the centroid is located at 4.5 inches from the x-axis. Now I mentioned this once already, but recognizing symmetry, the y-coordinates for the centroids of region 4 and 5 must be identical to those of region 1 and 2, which give us a y-coordinate for region 4 of 2.5 and a region 5 as 0.5. So moving on to step 4, for each individual region, we now need to take our second column, the area. We have to multiply that by our third column, which is the distance from the x-axis, the origin. And we need to plug this product into our final column in that table. And doing that, we get some manageable numbers, not so big this time. And for step 5, we move over to that area column. We actually sum up all these values. And when we do that, we get a value of 20. And for step 6, we do the same for summing all the products that we just calculated in step 4. And we get a value of 54. And that brings us again to our final step, where we now have all the data again to define what our y-coordinate is for our centroid of this composite object. So again, we're flipping back to page 67 for repetition's sake. We're looking at where those formulas are located. We're bringing those back over to our practice problem, as you see right there in the bottom right corner. And with the y-coordinate for this centroid, our only concern at this point, I highlight it. And plugging in our values, 54 divided by 20, we're going to get a y-coordinate for our centroid located at 2.7 inches up from the x-axis. So this completes our problem, and we can now define our ycg, y sub cg, or y bar. Again, whatever nomenclature you encounter, it'll be shown very many different ways, I'm sure. But whatever it is, the centroid of this composite object is located at 0 and 2.7 inches. So this is a practice problem right here where the centroid actually falls outside of the boundaries of this discrete object. Now, many students that I've worked with now over many years have gotten very confused when they find a centroid falls outside of an object. They think that the centroid needs to be located within the boundaries of that object, otherwise it's wrong. Now, understandable, but that's not the reality. If you guys find on the exam that you're calculating a centroid that falls outside the boundaries, don't think you did it wrong automatically. Don't look at the answer options of a problem before you even calculate it and subtract out or cross out those that fall outside the boundaries, because it's very possible that you will get an object with a center of gravity or a centroid that falls outside of the boundaries. So just remember that, and this is an example of just that.